If there's anyone listening on Zoom, thank you also, and please ask a question so we can see the robot in action at least once. Okay, so today I wanted to tell you about something I've been thinking about a lot in recent years, which is holomorphic motion. So what I'm going to present today is joint work with Tom Ransford and one of his former students. So I try to keep my talk as self-contained as possible because this is a very diverse group of participants, and the starting point of my talk will be quasiconformal mappings. Okay, so maybe we can start with the basics, just the definition. I don't think it's necessary, but just in case. So what's a quasiconformal mapping? It's a homomorphism of the sphere, let's say, which doesn't necessarily preserve angles, but it does preserve angles up to a bounded factor. So a generalization of conformal maps. And then one way to express this, this additional flexibility is to use this Beltrami equation. So here we have the analytic definition. So we start with some orientation-preserving homomorphism of the sphere. And then we say it's quasiconformal if it belongs to this Sobolev space, and then it satisfies this partial differential equation that we call the Beltrami equation. And this Beltrami equation involves some measurable function mu on the sphere with the L infinity norm strictly less than 1. So there's some kind of ellipticity for this PDE. And this function mu is what we call the Beltrami coefficient of the complex dilatation of the quasiconformal mapping. And you can think of this as some kind of measure of non-conformality of the map, because if you have, for example, a conformal map analytic, then the Cauchy-Riemann equations will tell you that the mu is just 0. And if the mu is 0 and you have a quasiconformal map, then it has to be conformal. This is a well-known property of quasiconformal mappings. Okay? And then some notation. So during this talk, I will denote k quasiconformal mappings, those quasiconformal maps that have the property that the norm of the Beltrami coefficient is at most little k. Okay? So there's usually two choices we can make when we talk about quasiconformal mappings. You can either talk about capital K, which is related to little k, but for this talk, I'll really focus on the norm of the Beltrami coefficient itself. Okay? Okay, so now we have these homomorphisms, and then they have these Beltrami coefficients, and it's actually surjective. So given any Beltrami coefficient, you can solve the Beltrami equation. That's a famous theorem in the area. So if you start with a measurable function with norm less than 1, you can always solve the Beltrami equation to get a quasiconformal mapping. And the solution is always unique up to composition by a conformal map on the sphere, so a Mobius transformation. Okay? Okay, so because of this Beltrami coefficient, this dilatation, quasiconformal mappings, they can distort the shapes or the size of sets in the plane. So they can change dimension, for example, or area. And there's been a lot of work trying to quantify exactly how bad this distortion can be. So maybe I can present some theorems related to this. So the first one is a classical theorem of Astala from 1994, who studied the distortion of dimension under quasiconformal mappings. So if you start with a little k quasiconformal map, and you start with a set A in the plane with positive dimension, let's say, then you can quantify how bad the dimension of the image can be. It has to satisfy these two inequalities, upper bound and lower bound. And here the capital K is related to the little k by the following formula. Okay? So that's one theorem about quasiconformal distortion that's well known nowadays. And then Astala also showed that these estimates are sharp in the following sense. So if you fix or you prescribe the dimension of the set, you call this T, then you can always find a k quasiconformal mapping which will attain the upper bound, let's say. And then the lower bound is also attained just by a symmetric argument. Okay? Okay, so now if you, what are other examples of these distortion theorems? Well, another famous one is due to Smirnov, and that's about the dimension of what we call little k quasicircles. So the idea is if you start with the set A to be the real line, then you apply a k quasiconformal mapping, you get what we call a k quasicircle, and then you can ask yourself what is the biggest dimension that this quasicircle can have in terms of little k. And if you start with Astala's estimate, you replace A by the real line, this will be 1. And then you'll get a lower bound from this inequality for 1 over the dimension, so that will give you an upper bound for the dimension itself. And if you do this, you do the calculation, you get 1 plus k. And now it was conjectured by Astala that this 1 plus k can actually be improved, so to 1 plus k squared. And this was proved by Smirnov in a pretty, another famous paper about 15 years later. So he showed that if you have a k quasicircle, then the dimension, a Hausdorff dimension, is at most 1 plus k squared. Okay? And then let me present another distortion theorem, this one about area. So that's a theorem that was proved by Astala, where the setting is the following. We start again with a k quasiconformal map, but we have the additional assumption that it has to be conformal outside of the disk and normalized in the following way. Well, if you start with a set inside the disk, a Borel set, then you can quantify how much the area can change when you apply your quasiconformal mapping. So it changes in terms of the dimension, the area of the set that you started with. There's some power, 1 over k, and then there's a constant here. So what Astala did is he proved this estimate for some constant depending on k, not explicit, and then Eremenko and Hamilton, they simplified the proof, and they got an explicit formula for this constant. Okay, so this constant here is due to Eremenko and Hamilton. Okay? And this estimate is also sharp. There are simple examples of quasiconformal mappings, like radial stretching, which will give you the upper bound. Okay? Okay, so for this talk, I'd like to discuss the following question. So if you look at all the proofs, so these are all different papers, the proofs are not trivial, but they all have sort of common ingredients. So one question we were interested in is there a sort of a unified approach to all of these quasiconformal distortion theorems? So just one proof that would somehow give you all of these results as corollaries. And what I want to talk about today is yes. So we're able to do this, and there's 2 main ingredients. So the first one is holomorphic motions, as in the title of the talk. And this is not new. This was used by Astala and Smirnov in all these papers. But the other new ingredient is this notion of inharmonic functions that we introduced. Okay? Any question so far? No? Okay, so that was sort of the introduction, the motivation. So now let me talk a little bit about holomorphic motions, and then we'll get a little bit later to those inharmonic functions. Okay? Okay, so the title of my talk is this, Miracles of Holomorphic Motion. And that's actually not a title that I came up with. It's the title of a very nice survey paper on the topic by Carrie Astala. And this is really the paper that got me interested in holomorphic motions. It's very, very nicely written and almost poetic, as you will see. So I would like to start with a quote from that paper that sort of explains the philosophy behind these holomorphic motions. Okay? So what Astala wrote is the following: what draws us to mathematics maintains its spell upon us. A beautiful example are no doubt the holomorphic motions discovered by Manoa, and Sullivan that have held their magic since their invention in the mid-1980s. So Astala continues, the notion can be explained in a few lines to anyone. It's basically a deformation of the space with a non-standard concept of time. Time is assumed to vary holomorphically. Nothing more is assumed, and yet the conclusions are very strong and unexpected. One cannot avoid an everlasting astonishment. So pretty strong words from Carrie here. And this is sort of the philosophy that I would like to convey in this talk, that holomorphic motions are very beautiful, and then it's sort of magical what you can prove with so little assumptions. So the ratio of the things that you can prove over the assumptions that you need is very high. And I think that's why I got interested so much in this. Okay? Okay, so what's the definition that we start with? It's the following. So we start with a set A in the sphere, and then we define a holomorphic motion of that set to be a map of 2 variables. So there's one variable that lives in the disk, another one that's in the set A. So I'll call lambda for the variable in the disk and z for the variable in A. So the first condition is that if you fix z, then the holomorphic motion should be holomorphic in lambda as a function on the unit disk. The second condition is if you fix lambda, then this map should be injective in z, and then it should start at the identity when lambda is equal to 0. Okay? So those are the only assumptions, holomorphic in lambda, injective in z, and it starts at the identity. So in particular, there's no assumption on the behavior of f as a function of the pair lambda z, the joint behavior. Okay? It's just separately holomorphic and injective. And now just some notation I'm going to use, which is pretty standard when you talk about holomorphic motions. So if you fix lambda, then you get a map f lambda z, a function of z, and I'm going to denote this by f sub lambda. So the only assumption we have here from the definition is that this is an injective function on the set A. Okay? And then another thing I will do is I will always assume that those maps, if lambda, they fix 0, 1, and infinity. We can assume that by composing with a Mobius transformation if necessary. It just makes the theorems a little bit nicer. Okay? Okay, so that's the definition. So why were we interested in those holomorphic motions? As Astala mentioned, it comes from a paper of Manoa and Sullivan from the 1980s. And what they did is they observed that Julia sets of rational maps often move holomorphically, so they're often part of one of these holomorphic motions, if you have some holomorphic variations of their coefficients, the coefficients of the rational map. Okay? So here's a sort of an illustration of this. So here on the left, you have the Mandelbrot set. So if you look at the main cardioid, for every parameter inside of the main cardioid, you get a corresponding Julia set. It's a Jordan curve. And the observation by Manoa and Sullivan is that as you move around the parameter C, the Julia set changes, but it changes as part of a holomorphic motion. So there is some strong dependence in terms of the parameter C if you're interested in the structure of these Julia sets, at least for the main cardioid of the Mandelbrot set. Okay? Question about it? Okay, so that was the observation. Let me continue with another nice quote from this paper. So Astala continues, and he says, in practical terms, we're discussing deformations with no assumptions at all on the space variable, just injectivity. So there's no continuity assumption or not even measurability, while the key property is the holomorphic dependence required from the time parameter lambda. As innocent as this mere last assumption may appear, let us see how far it can take us and be ready for surprises. Okay? Yeah, it's like reading a novel. It's very, very interesting. Okay, so what kind of surprises is Carrie talking about? Well, one of them is this so-called lambda lemma. So this was proved by Manoa Sullivan in that same paper. And they showed that if you start with a holomorphic motion of a set, you can always extend this motion to a motion of the closure of the set. And not only this, but this extension that you get is jointly continuous in the pair lambda z. So even though you start with no joint assumption at all, sort of magically, because of the holomorphic dependence and the injectivity in z, you get this joint continuity for the holomorphic motion. Okay? And a couple of years after that, there's, another quote. That's the last one, I think. So the Manoa-Sullivan proof was so simple and the results so unexpected that, to be honest, upon seeing the argument, each of us complex analysts stood in bewilderment. How is this even possible? Okay, okay, so that's the lambda lemma. You can always extend to the closure of a set. And then it was conjectured a couple of years after that by Sullivan and Thurston that every holomorphic motion should in fact extend to a motion of the whole Riemann sphere, not just the closure of the set. And this was proved in a remarkable paper 5 years later by Slatkovsky using methods of several complex variables. So Slatkovsky showed that every motion, you can always extend it to a motion of the whole Riemann sphere, whatever the set you start with and whatever the motion you start with as well. Okay? Which is, again, a very unexpected property for such simple assumptions. Okay, so now we can, maybe I can just go back, recall the definition. So if you look at these maps F lambda, they were only assumed to be injective, but because of the lambda lemma, we know that they're continuous. So if you have a motion defined on the whole sphere, like here, what you can do is you can look at those maps F lambda, and now you know that they're homomorphism, they're injective, and they're continuous. And one can wonder what is the precise degree of regularity for these maps F lambda that you get out of the holomorphic motion. And even if you don't know the answer, you probably can guess it by now. So the regularity is that they have to be quasiconformal mappings, which is, again, kind of magical. You start with just injective, and you upgrade this to quasiconformal, okay? So we have this theorem, which is sometimes referred to as the extended lambda lemma. So if you start with a function of lambda z, then it will be a holomorphic motion if and only if it's essentially a family of quasiconformal mappings that depend holomorphically on the parameter lambda. In the sense that if you fix lambda, then each of those maps F lambda is quasiconformal, and a little k is given in terms of lambda by the absolute value. And moreover, if you look at the Beltrami coefficients of those QC mappings, they vary holomorphically with respect to the parameter lambda, okay? So that gives two important consequences. The first one is if you start with a quasiconformal mapping, you can always embed it into a holomorphic motion, which is a consequence of this. And then the other consequence, as you can see, is that holomorphic motions of the whole sphere, you can just think of them as families of quasiconformal mappings that depend holomorphically on some parameter lambda. So there's this very strong correspondence here. If you can prove results about holomorphic motion, then you can deduce properties about quasiconformal mappings and vice versa. Okay? And this is what Astala and Smirnov and these people did to study quasiconformal distortion. Okay? Okay, question about holomorphic motions? No? So that was pretty much the basics of what we know about them. I wanted to mention, because this is a workshop about probability also, so there's a connection between holomorphic motions and Loebner theory. So I learned this from a nice paper by Tran from 2017. I don't think it's published. Is that correct? You don't? Yeah, okay. And so what Tran did is he studied the Loebner equation driven by a complex valued function instead of a real valued function. So you looked at this Loebner equation here, where the driving function is complex and it depends on some parameter alpha, which lives in the unit disk. So the idea is to start with a suitable 1/2 Holder function, so that we know that if we solve the Loebner equation, we get a quasi-arc. And then to multiply this by some parameter lambda and see how the solution changes in terms of this complex parameter lambda. And then what Tran showed is that you get a holomorphic motion out of this, holomorphic motion of a line segment. Okay? So just a question that crossed my mind. So I was wondering what happened maybe if you replace this 1/2 Holder function by Brownian motion, some kind of version of SLE, but with complex parameter kappa. Of course, there's no reason to expect a holomorphic motion out of this, but I'm kind of curious what would, if you can say anything interesting about what you get here. So as far as I know, there's only one paper I was able to find by Ewan and Pfeffer on this subject. So maybe you can tell me more at some point about this. Okay, so that was the probability part of this talk. Okay, so now let's go back to the original question, or what I want to discuss is sort of the following question. So you start with a set-valued function. So that's a real valued function defined on subsets of the plane. And then you start with a set, and you start with a holomorphic motion. So what you can do is you can move your set around using the motion. So you apply F lambda to the set A. And then you see how does the set function changes when you do that. Okay, the set function could be dimension, for example. And what you're looking at is how does dimension changes under holomorphic motion. Okay? And that's a very general question that was studied extensively in the past. So there's been a lot of work that was done on this question, either by looking at a specific set function, like dimension or area or things like that, or looking at specific holomorphic motions coming from dynamics, for example, or Kleinian groups, or looking at specific set A, like a Julia set or a limit set of some dynamical systems. So for example, there's this very famous paper by Ruel where he studied this question, where A is the Julia set of a hyperbolic rational map, and F is Hausdorff dimension. And then that was the paper that introduced thermodynamic formalism to show that with some hyperbolic condition, these Julia sets dimension change in a real analytic way, okay? Which is true for the main cardioid of the Mandelbrot set, for example. And then after that, there's been a variety of papers on this question for different choices of these functions. Okay? And I try to summarize some of the results that I was interested in the following table. So here on the left, you have a choice of this set function f. So for example, it could be S-dimensional Hausdorff measure, it could be area, it could be any notion of dimension you want to study, like Hausdorff packing or Minkowski. It could be a notion of capacity. We've heard before in this workshop about logarithmic capacity, and there's other notions like analytic capacity. And for each of these, you can study how they change under holomorphic motions. And now the first thing you can ask yourself is, does it change in a continuous way? So is this a continuous function of the parameter lambda? For Hausdorff measure, the answer is no. You can come up with easy examples, like Julia sets of some polynomials. It's not difficult to see. But for a lot of them, it does vary continuously. That's the case, for example, for area, for a lot of the notions of dimensions. It's the case for logarithmic capacity. It's not the case for analytic capacity. And if you know it varies continuously, then you can ask yourself, well, what is the precise degree of regularity? And then in this column, I try to indicate if the answer is known. So for area, we don't know. And for some of the dimension we know, like packing, that's just part of the work that we do. Yeah.
What do you mean by regularity?
Yeah, so you have a function of lambda, and then you just ask yourself, what is the regularity? Is it better than continuous? Is it differentiable? Is it real analytic, for example? But here the thing is you don't have any assumption on the set and you don't have any assumption on the holomorphic motion. So that should be a very general theorem. Yeah. Does that make sense? Okay. Okay. And so for the rest of the talk today, I'd like to focus on these dimensions and try to explain the results that we obtained for those holomorphic motions, and then explain how these results can give us a sort of a unified approach to these quasiconformal distortion theorems that I started with. Other questions? No? Okay. So maybe we could start with logarithmic capacity. It's a little bit easier to study than dimension. And hopefully it will give us some insight into the question. So the definition that's more convenient for us to use is the definition in terms of transfinite diameter. So you start with a set E, and then you look at the product of pairwise distances with points in the set. You normalize by taking some exponent, and you try to maximize these pairwise distances. That's what we call the nth diameter. And then there's a classical theorem of potential theory that this is always a decreasing sequence, and then in the limit, you get the logarithmic capacity. If you want, you can use this as definition of logarithmic capacity. It's sometimes called a transfinite diameter as well. And so what I want to explain now is how we can study a variation of logarithmic capacity under holomorphic motions using this transfinite diameter definition. So that's part of a paper that we wrote a couple of years ago, where we showed that this logarithmic capacity, if you have a holomorphic motion and you have an arbitrary compact set, then the capacity always changes in a continuous way. And here's the idea of the proof. So first, you can assume that the set is infinite without loss of generality. And then if you take n distinct points inside of the set, then you can look at the following function. So what is this function? You have the product of f lambda applied to pairs of distinct points. So this will be a holomorphic function in lambda, because if you fix z, holomorphic motion is holomorphic. And also because f lambda is injective, and these are distinct points, so this is non-vanishing. So what you have here is the log of the absolute value of a non-vanishing analytic function, and that's always a harmonic function on the unit disk. Okay? Now, if you know that this thing is harmonic, then you can easily deduce the same thing for, essentially the same thing for the n diameter, except that you may lose harmonicity, but you can write the n diameter as the infimum of a family of harmonic function. Well, you have to take the log and then the minus. So in the n diameter, there's a supremum, so you would get supremum, but because you take the minus, you get infimum of harmonic functions. Okay? And now if you have an infimum of harmonic functions for this function, well, because the n diameter decreases to the logarithmic capacity, what you get is you can get the same thing for that function, minus the log of the capacity of the holomorphic motion. And now that's the key observation, is if you have one of these functions, an infimum of harmonic functions on the disk, you can normalize a harmonic function so that they're positive. And what you get in the end is you get something that will satisfy a Harnack inequality, because harmonic functions on the disk satisfy Harnack inequality, and that remains true if you take the infimum as well. And out of this Harnack inequality, you can deduce the continuity of the function. It's also not difficult to do. Okay? So the precise details are not important. Just keep in mind that we wanted to study variation of something under holomorphic motions. And what we did is we deduced some information about the function by writing it as an infimum of harmonic functions. These are the inf harmonic functions that I mentioned. Okay? Okay, so now let's go back to this more interesting question. How does the dimension changes under arbitrary holomorphic motion? And here for dimension, you can consider any reasonable notion of dimension you want to study. It could be Hausdorff, or it could be packing, or upper Minkowski, for instance. So you start with the set A, you move it around under a holomorphic motion, and you try to study how the dimension of the set changes. Okay? So I think now I have a couple of slides where I recall the definition. I'll just go through them quickly. So this is Hausdorff dimension. We're all familiar with this. So you look at, it's defined in terms of coverings of your set of diameter at most delta, and then you take delta smaller and smaller. This is Hausdorff measure. And then the Hausdorff dimension is the critical value where the Hausdorff measure goes from infinity to 0. Maybe you're less familiar with packing dimension. So this is sort of a dual notion to Hausdorff, where instead of considering coverings, you consider packings. So you try to pack disks inside that are centered at inside your set that are disjoint, and the diameter is at most delta, and then you take delta smaller and smaller possible, and you try to maximize the sum of the diameters to the power s. So it turns out that this is not a measure, so there's a classical trick to turn this into a measure, is you try to find an optimal covering, optimal in the sense that you try to minimize this pre-packing measure. And now this is a measure, so you can do the same thing as we did for Hausdorff dimension, where you look at the critical number s, where the packing measure goes from infinity to 0. Okay? And then there's also Minkowski, another notion of dimension. So you have the definition. I don't really have anything interesting to say about it. The only thing that maybe you don't know is that they're related by this inequality. So the upper Minkowski is always the largest, followed by packing, and then Hausdorff dimension is the smallest of the three dimensions. Okay? Okay, so now, before I state the main results, the question that we're trying to answer is this one. Well, it's not clear what kind of answer we're going after. So how can we get information about what we're trying to prove? Well, we can go back to the estimates by Astala for this. So if we go back to the estimates of Astala, so you start with a quasiconformal mapping, and then Astala gives us an equality for the dimension of the image of A under the QC mapping F. Now, if you remember, every quasiconformal mapping can be embedded into a holomorphic motion. So you embed F into a holomorphic motion. And now you get estimates for the dimension of the holomorphic motion. So this is a function we want to study here, dimension of F lambda of A. And now something that took me a long time to realize, but it's very simple, is that if you look at this inequality, this is exactly Harnack inequality applied to a specific function. It's just Harnack inequality applied to 1 over the dimension minus 1/2, right? So this is the function at lambda. This is a function at 0. F0 is the identity. And then you have the usual Harnack constant 1 plus lambda over 1 minus lambda, and same thing on the left-hand side with the reciprocal. Okay, so what's the point of this? Well, if you're able to show that for any holomorphic motion and for any set, this thing always satisfies Harnack inequality, basically that gives you a new proof of Astala's inequalities. Okay? That's what I'm trying to explain here. So what we're looking after to describe this function is something that satisfies Harnack inequality, essentially. Now, how can we hope to get Smirnov's theorem out of this? Well, this is, I can say a bit more about it later, but the idea is that in the special case when A is a real line, there's some additional symmetry. And then because of this additional symmetry, we were able to use some improved Harnack inequality. So the idea is that this lambda, you can improve it by a factor lambda squared. And that's for our holomorphic motion. Now, if you want to recover a specific QC mapping, you have to set lambda to be equal to k. And if you look at the lower bound you get when you do this is that, then you can simplify, and that gives you a lower bound for 1 over the dimension. You flip this around, you get the 1 plus k squared. That's exactly Smirnov's theorem. Okay? So basically, if you can show that this always satisfies Harnack inequality, you get Astala's estimates, and if you can show that with the additional symmetry you have an improved Harnack, then you get Smirnov's theorem. Okay? And what kind of functions satisfy Harnack inequality? I talked briefly about them when we talked about logarithmic capacity. These are the infimum of harmonic functions. So that's what we call inf harmonic function. If you have a positive function, then we call it inf harmonic if it can be written as a pointwise infimum of a family of positive harmonic functions on the disk. Okay, questions so far? So these inf harmonic functions, they're continuous, but they also have some nicer properties. I already mentioned that they satisfy Harnack inequality. From this, you can deduce continuity. And because they're infimum of harmonic functions, they turn out to be superharmonic. So they also satisfy some minimum principle, for example. Okay? So a little bit better than continuous, but not necessarily differentiable. Kind of in between these two classes. Okay? All right, so now I can state our main results. So the first one we have applies to packing or Minkowski dimension. And we were able to show the following, that if you start with any holomorphic motion in any set, no assumptions at all, then this function 1 over the dimension, and then you normalize by subtracting 1/2, is always one of these inf harmonic functions. Okay? So in particular, this gives you Harnack inequality for this, and as we mentioned, this gives you another proof of Astala's estimates for packing this dimension or Minkowski dimension. Okay? So that's the first theorem that we have. Then we also have a converse theorem that we were able to prove. So basically, you can prescribe the dimension function as long as it has the correct regularity. So 1 over the dimension function should be inf harmonic, but if you give me such a function d, then I can realize it as the variation of dimension under some holomorphic motion for some compact set A. And that converse applies to Hausdorff dimension and also packing dimension. So an interesting consequence of this is you can have holomorphic motion where the dimension changes with very little regularity, because these inf harmonic functions, they can have very little regularity. So for example, if you look at this corollary here, so if you start with any concave function, then you can find a holomorphic motion whose dimension changes according to essentially the reciprocal of this concave function. So dimension, the variation of dimension under holomorphic motion essentially can have the same lack of regularity as an arbitrary concave function. Okay. So we have this converse result as well. The only thing that's kind of missing in our work is if we go back to the main theorem, it applies to packing or Minkowski, not Hausdorff. And the converse applies to packing and Hausdorff, but not Minkowski. So the common denominator is packing dimension, so that's why I wrote here that we obtain a complete answer for the variation of packing dimension under this holomorphic motion. But unfortunately for Hausdorff dimension, we were not able to get a similar result, so the best that we have for Hausdorff dimension is the following. So if you look at the function, 1 over the Hausdorff dimension minus 1/2, we don't know if it is nth-harmonic, but our method gives us that it is the supremum of a family of nth-harmonic function, like a sup nth-harmonic functions if you want, which is not necessarily the same thing as just nth-harmonic, is not as good, but it's enough to get Harnack inequality though. These functions, they still satisfy Harnack inequality, so you can still recover the bounds of Astala for distortion of dimension, Hausdorff dimension under quasiconformal mappings. Okay? And now the question that remains is it nth-harmonic? We still don't know. So the difficulty is, so packing and Minkowski, they're defined in terms of packing, and there's an infimum in the definition, but for Hausdorff dimension, it's a supremum, and because of that, it's like the inequalities go in the wrong way. So we're not really able to improve to get rid of the supremum here. There's an inequality at some point that goes in the wrong direction, and we don't know how to get around this. So that's still an open problem. And if one were to answer this question, then it would give a complete description for Hausdorff dimension as well. Okay?
Are you hoping for more than nth-harmonic or just nth-harmonic?
No, because I mean, yeah, because of this converse result, that's the best that you can hope for, right? Yeah. So at least for Hausdorff dimension. Yeah. Okay, other question? Okay, so as I mentioned, that gives sort of a unified approach to these quasiconformal distortion theorems. So what we can do with this method and nth-harmonic functions and holomorphic motions is to reprove all of the Astala's bounds and also Smirnov's theorem for all 3 dimensions, packing Hausdorff and upper Minkowski. In particular, this allows us to prove that the upper Minkowski of a k quasicircle is at most 1 plus k squared, so that's sort of an improved estimate compared to Smirnov's. And then we also, recently, with my PhD student, Catherine, we proved similar results for another version of dimension called Aswad dimension. I call it the GOD, the greatest of all dimensions, because it's literally the greatest of all dimensions. It's bigger than Minkowski and bigger packing, bigger than Hausdorff. So that's what we're working on right now. And then if we're able to do this, that would also give us that the upper Minkowski, the Aswad dimension of a k quasicircle is at most 1 plus k squared. But this part is not fully written down yet. But we know that we have an nth-harmonic theorem for Aswad dimension. So this part is written down. I did not have the time to talk about it. I did mention it at the beginning of the talk, but there is this theorem of Astala and also Eremenko-Hamilton on the distortion of area. And we were able to also get a new proof of that theorem using the nth-harmonic functions and holomorphic motion.
Did they actually also use motion?
Yeah, they did. Yeah, that's right. Yeah. And yeah, I guess the main question is why we're reproving these theorems. But one reason is because we wanted a unified approach, but also if you look at the proofs of these theorems, a lot of them use some of the harder analytic properties of quasiconformal mappings, like optimal Sobolev regularity. So quasiconformal mappings are W1, 2, but the 2 can actually be improved to something a little bit better. But doing this requires a lot of work. That's what Astala did. And from this, he proved these bounds on the distortion of dimension and area. But the approach that we have, we don't need any hard analytic properties. So the only thing we use about quasiconformal mappings is some kind of quasisymmetry property, weaker than quasisymmetry, in fact. Okay, let's see how, 5 minutes? Okay, perfect. Yeah, just to finish the talk, I wanted to mention something I've been thinking about, and it's in relationship to an open problem about quasiconformal deformation of the Sierpinski carpet. So this is sort of related to something that I know some of you have thought about before, which is the conformal dimension of the Sierpinski carpet. So that's a famous open problem, which is probably difficult, but hopefully this question, it's also open, but hopefully a little bit more easier. And the question is very simple. Is it possible to decrease the dimension of the carpet by a quasiconformal mapping? So it's still unknown whether it's possible or not. So what I've been working on with one of my students is to try to approach this question by using holomorphic motions. So basically you apply holomorphic motions to the Sierpinski carpet and you try to see what you can say about the dimension of these holomorphic deformations of the carpet. So the idea is that if the answer to this question is no, then that would mean that this is always greater or equal for any quasiconformal mapping. That would tell you something about holomorphic deformations of the carpet. You would get that the dimension of any holomorphic motion of the carpet basically always has a minimum when lambda is equal to 0. So 1 over the dimension always has a maximum at the origin. So what you would get is you would get all of these infinite functions that always have a global maximum at 0. And what we're trying to do is start with an infinite function that does not have a global maximum at 0 and try to realize it as the dimension of a holomorphic motion of the Sierpinski carpet. If you can do that, then you can answer this question here. Okay? Okay, I think that's all I want to say. So thank you very much.